So we've got a problem here. We know how to write logical formulas using and, or, and not, but it turns out there are many different formulas that define the same function, and it would be nice to agree on a single way of expressing a specific function. The same sort of situation arises with polynomial functions, and you learned one solution back in middle school. If you multiply out all the products, as I've done here, expanding the square, expanding the product, eventually you can write a polynomial in any number of variables as a sum of monomials. You can think of OR as being kind of like addition and as being kind of like multiplication, and do exactly the same thing. The jargon for this is disjunctive form. Up here, this fully expanded polynomial was a sum of products, and in disjunctive form we have an OR of various terms formed using only AND. So here's an example with 4 logical variables P, Q, R, and S. This is in disjunctive form because there's an AND in the first factor, an AND in the second factor, an AND in the last factor, and then we're ORing those together. The alternative doesn't always work in ordinary algebra, but from time to time you can take an expression and factor it completely, and when you factored it completely, you've set it up in such a way that you do all the addition first and then do all the multiplication. Turns out this is always possible with logical functions, and it's called conjunctive form. A logical expression is in conjunctive form if you do all the ORs first, followed by the ANDs. In other words, if your expression is an AND of terms that use only OR. Here we have one, P or Q, and P or R, and Q or not R, and S. And in both these forms, the not goes with individual variables. However, this is not the best way to write expressions. A better solution than disjunctive form is what we're going to call disjunctive normal form. This was a big deal the year that I taught CS20, and this was the terminology used by the textbook in that course. What makes disjunctive normal form as opposed to just disjunctive form is that each of these individual AND terms has to include each variable or the negation of that variable. This is best illustrated by an example. Got a function of P, Q, and R, and you say this function is defined as Q and not R. We're doing the ANDs first, and there aren't any further ORs to do, but arguably this is in disjunctive form, but it's not in normal disjunctive form because it doesn't mention P. And in order to convert it to disjunctive normal form, all we do is to write it as either P and Q and not R, or not P and Q and not R. If you make a truth table for this, there are going to be 2 lines in the truth table that lead to the value true. You get one line where P and Q are true and R is false. You get another line where P is false, Q is true, R is Q. And if you look, it's apparent that each of these lines corresponds to one factor in the disjunctive normal form. You've probably now already guessed what conjunctive normal form is going to be. It's like conjunctive form in the sense that it's an AND of OR terms, but each OR term now has to include each variable, or the negation of that variable. So here's one. I sort of messed this up, but I'll fix it. It was meant to be Q or not R, and the problem is that P is not mentioned. And the way I'm going to fix that is to say this is either P or Q or not R, or not P or Q or not R. That's in conjunctive normal form. And in this second example, there are going to be two false lines in the truth table. You can get false if P and Q are false and R is true, and that corresponds in a rather subtle way to this first term here. You can say if either P is true or Q is true or R is false, this line can't exist. So we're going to rule that out, and similarly we're going to rule out the second line by saying that second line can't occur if P is false or Q is true or R is false. And we say if we've ruled out the first false line and we've ruled out the second false line, then what remains must be true. People usually find this an order of magnitude harder to understand than disjunctive normal form. So what do we do with the truth table? Let's look at a simple example. Here's the truth table for the exclusive OR operation, and we can try writing it in both sorts of normal form. Let's first go for disjunctive normal form. For disjunctive normal form, we look at the true lines, and we say this is either P is true and Q is false, or the other true line, P is false and Q is true. For conjunctive normal form, we focus our attention on the false lines. We say if this is going to be true, well, we can't have the conditions for false line number 1, so we have not P and Q, and we also have not, looking at the other false lines, not P and not Q. But this isn't in conjunctive normal form yet because we don't have any ORs. The way you get the ORs in is you take the not and move it inside the parentheses. In accordance with De Morgan's law, when you do that, you change and to or, and you negate each individual factor. So we now have not P or not Q and P or Q. That means that exclusive OR of P and Q is true if P or Q is true, that rules out that line, or if either P or Q is false, that rules out the top line. Actually, you can do this directly by thinking about killing one of the input conditions for each false line. So if I want to write down the conjunctive normal form directly, and you're going to get practice with this very, very soon, you say, I look at the top false line and I say, the conditions for this false line cannot occur if P is false or if Q is false. And then for the other false line, the conditions for this cannot occur if either P is true or Q is true. Here's a simple function. F of P, Q, and R is equal to R. That's not in any sort of normal form because it never mentions P and Q, but we can fix that very easily. If I want to write it in disjunctive normal form, I just look at the 4 true lines and say this function is going to have the value true if P, Q, and R are all true, and then I combine the other 3 possibilities for P and Q with R. If I want conjunctive normal form, I have to look at the false lines in the truth table. Let's look at the very last one. If P is Q, true, or Q is true, or R is true, then the last line can't occur. So this corresponds to getting rid of line 8, and you can check for yourself that the other 3 false lines are disposed of by the other 3 terms. So here is one of my first endeavors in writing an app in Shiny. Shiny is designed to make it possible to write apps with a rather nice looking user interface, sort of like a standard web application. And later on in the course, if some of you are interested in learning how to do this, I will run some little classes. Here what we're trying to do is get practice in converting a truth table to disjunctive normal form or to conjunctive normal form. And we might, for example, have something specified by a logical formula that's not in either sort of form. For example, P or Q and R. So when I click the button, I discover I get true in all the cases where P is true, and I also get true in the case where, although P is false, both Q and R are true. I'm going to go for the low-hanging fruit and therefore try to write this in conjunctive normal form by looking at the false rows. And in writing the app, I tried to minimize the amount of typing that's necessary by putting in an and of ors to start with. So let's look at those last 3 lines. We can rule out this line if P is true, or if R is true, or if Q is false. We can rule out the next line if P is true, or Q is true, or R is false. And we can also rule it out if any of those 3 is true. When I think I've got this right, I click Test CNF, and the fact that the function that was generated by evaluating this formula agrees with F shows that I've got it right. If you want to play around with this yourself, it's even more fun to generate a random truth table. Let's get one with a bunch of true lines. There's a nice one. It's got only 2 true lines, so the disjunctive normal form is the easy case. You say, in disjunctive normal form, either I want P is false and both Q and R are true, or P and R are false while R remains true. And I click on the Test DNF button, and I've got it right. You can play around with this on your own. It's in the week 1 directory. You just put it into RStudio, click Control-Enter, and you can play with it to your heart's content. Now let's deal with the thorny issue of implies, because lots of logical expressions are of the form P implies Q. What does that mean? If I tell you that P implies Q, then the only way that you can show that I lie is by exhibiting a case where P is true, but nonetheless Q is false. In other words, the statement that P implies Q is equivalent to the statement P and not Q is false. And the negation of that statement, namely not P and not Q, therefore must be true. So P implies Q is equivalent to the negation of P and not Q, and by De Morgan's law, we move the not inside. Not Q is the same as Q. We change and to or, and here is the truth table. P implies Q is true when P and Q are both true, and it's also true in every case where P is false. The Hubbards bring this up in chapter 0 of their book, where there's a statement that says all 11-legged alligators are orange with blue spots. Or, written in terms of implies, the statement an alligator has 11 legs implies that alligator is orange with blue spots. That is a true statement, and in fact it remains a true statement no matter what you replace Q by, even something that is manifestly false, like the alligator is both a reptile and a mammal. Now let's prove the famous law of contraposition, which you've learned how to use in proofs. Not Q implies not P is equivalent to P implies Q, and here's the proof. Not Q implies not P. What does that mean? It means either you have the negation of the first premise, not Q, or you have the conclusion be true. So just as P implies Q gets turned into not P or Q, so not Q implies not P gets turned into not Q or not P. Well, not Q is the same thing as Q. We can turn the order of factors around in an or. We get not P or Q, which, as you already know, is equivalent to the statement P implies Q. So now you're getting some insight into how one can prove formal theorems of logic using Boolean algebra. Another important form of implies is if and only if. Here's the truth table for if and only if. The only true rows are the ones where P and Q are both true or both false. P if and only if Q. As with any logical formula, we can write this either in disjunctive normal form or conjunctive normal form. Let's try it both ways. Disjunctive normal form, as you've now realized, is very easy. You just look at the true lines and you say this is true if P and Q are both true, or if P and Q are both false. Conjunctive normal form is a little bit trickier. The easy way to do it is to say we want to rule out the false lines. So looking at this first false line, we say we're going to rule out the line where P is true and Q is false, and we're also going to rule out the line where P is false and Q is true, and then you apply De Morgan's law, move the not inside, change the and to an or. This first factor turns into not P or Q, and the second factor turns into P or not Q. And that's another way of looking at if and only if. What it basically says is you rule out both the cases where one of these is true while the other is false. But there's another way of writing not P or Q. It's P implies Q. So another way of writing if and only if is P implies Q and Q implies P. It's true both ways around, and that's probably the most natural way of doing it. That concludes our little exercise in writing logical expressions using Boolean algebra in standard form. I will follow this by showing you how to do this all in a much simpler way using finite fields.